Now, here we've been talking about light as a photon, as a collection of particles, and that's how we've been considering them as we think about energy and momentum and whatnot. But as we talked previously, we're talking about them as waves and talking about interference patterns and ray tracing and things like that. We were treating light as a wave, and so then the question is, which is it? Is it a wave or a particle? And the answer is not so simple. It turns out that light behaves like a wave in some cases, and in other cases it behaves like a particle. This is known as the wave-particle duality. That light kind of simultaneously acts like a wave and acts like a particle. So this guy, they discovered that light was a photon, and that worked pretty well. This guy named de Broglie, and it looks like de Broglie, but I think it's pronounced de Broglie. This guy named de Broglie came up with this idea. De Broglie said, hey, light, which we've traditionally thought of as a wave, acts like a particle. Acts like a particle. So, can a particle act like a wave? And this was de Broglie's, his hypothesis was that a particle would act like a wave. It would experience wave behavior, and it would interfere. And he did some math, and light, we know just from a minute ago, or from the previous video, sorry, has a momentum of h over lambda, and one can rearrange this to say lambda is h over momentum. Okay, and so then de Broglie hypothesized that matter would have a wavelength that was equal to Planck's constant over its momentum. So he said, well, why can't we, if light is a particle, why can't we apply this equation to other particles? And this seemed and probably still seems kind of ludicrous on the surface. It doesn't make sense for us to think about like baseballs or us, our bodies having a wavelength. But if we look at this, as momentum increases, wavelength decreases, right? So as this number gets bigger, this wavelength is going to get smaller. And h is a really small number. It's 10 to the minus 34th, on the order of 10 to the minus 34th. So if we have a momentum that's, like a whole number, that's not a very small fraction, like our bodies can have momenta, that are certainly larger than 1, then this wavelength winds up being a very small number, right? So it would make sense that we wouldn't notice the wavelength of macroscopic objects because they have momenta that are reasonably large, and h is a very small number. And so unless this momentum is also very small, this wavelength doesn't create any sort of noticeable effect. Okay? But still, it's a very strange idea to consider that a particle could have some kind of wavelength. So they've done experiments since then, and one thing that was done was that the two-slit experiment. Remember, Young made this two-slit experiment and saw that light interfered, and then, he thought conclusively proved that light was a wave. And well, it interfered. It is a wave, but it's also a particle, as Einstein discovered. But this two-slit experiment was then repeated later with electrons. And when you do the two-slit experiment with electrons, you put up a detector, and you get this pattern where electrons, there'll be electrons hitting, and then there's a gap where they don't hit, and then they hit again, and there's a gap where they don't hit. And this, is the same thing as that interference pattern of maxes and mins that we saw with our light. Where all these electrons are hitting, that's a max in the wave, and then they here they interfere, that's a minimum. Here they don't here they interfere constructively, that's a maximum. Here they interfere destructively, that's a minimum. Constructive, and so forth. And so that interference pattern actually occurs when you shoot electrons at the two slits. So there is some sense in which this de Broglie wavelength corresponds to a real thing. These electrons can interfere with each other, which is a very weird thing that we'll talk about more later. But first off, I just want to just give you some numbers here. So let's say we've got an apple that has a mass 0.13 kilograms, 130 grams, and it's moving at 5 meters per second. Okay. We know that momentum is half mv squared, and that extra effect that I was talking about from relativity, where you change the momentum formula, that's only significant when this velocity gets close to the speed of light. So we can just go ahead and use this half mv squared when objects are not anywhere near the speed of light. And so that's half 0.13 times 5 squared, and we can stick that into our calculator and get a momentum. Now, the de Broglie wavelength is equal to h over momentum. So we've got Planck's constant over our half 0.13 times 5 squared. And if we plug those numbers in, we get a value for the de Broglie wavelength of this apple that is about 1.0 times 10 to the minus 33rd meters is the de Broglie wavelength of this apple. Now, 10 to the minus 33rd meters is a really, really small wavelength. Atoms have size on the order of 10 to the minus 10th. Excuse me. So if something has a wavelength this small, it stands to reason that we wouldn't be able to detect it exhibiting any sort of wave behavior, like interference, for example. In an interference pattern where the wavelength is this small, the interference pattern, like the maxes and mins, would be so closely spaced that we wouldn't even be able to detect them. Okay. By comparison, an electron with kinetic energy of 10 electron volts, which is a fairly reasonable value for the kinetic energy of an electron in an atomic system. It has a wavelength of 3.88 times 10 to the minus 10th meters, which again, that's still really small, but this 10 to the minus 10th is on the scale of the size of an atom. And so if a wavelength is the same scale as, the size of the space that you're occupying, then that becomes a significant effect. So you can see how this de Broglie wavelength can be significant with things like electrons that are really small, but essentially make no difference in macroscopic objects, which is why it took so long to recognize that there was anything different than Newtonian stuff going on. And it wasn't until we got objects going really fast, like close to the speed of light, and until we started dealing with things that were really small, that these problems with Newtonian mechanics were discovered, because Newton's laws and whatnot work very, very well for the objects we deal with on an everyday basis.